Hello, we are the Life Savers, a multidisciplinary senior design team in the Kate Gleason College of Engineering. Coming from different departments and backgrounds, we were able to work together to accomplish more than any of us could individually.
NASA is planning to use the Orion spacecraft to visit the Moon in 2024. In the case of an emergency during the mission, Orion crew members will exit the vehicle on a life raft. Currently, if members of the crew become separated, NASA's search and rescue team must manually locate them, which would lead to the rescuers getting split up and wasting time in lieu of saving them. The key goals of this project are to design an unmanned vehicle that can withstand a 15-foot drop into a maritime environment via a UAV, autonomously travel to, and subsequently deliver supplies to stranded astronauts. The goal is to decrease the time it takes search and rescue to deliver supplies to each separated crew member.
Our stakeholders are interested in a robust and comprehensive solution that helps to expand the area that can be covered for search and rescue operations, withstand a 15-foot drop in a marine environment, and deliver supplies to stranded astronauts. In addition, the end product should adhere to each of the following requirements shown on this graph.
Our saver device needs to withstand a 15-foot drop and be dropped into a maritime environment in order to detect a beacon signal from a lost astronaut. So for our approach to the solution, we decided to go with a polycarbonate hull in order to withstand the impact it'll receive when it hits the ocean. There is two compartments, one in the front for supplies and one in the back for electronics, and both of them will be sealed off from each other. You can see the Doppler antenna array on the top. That's going to locate the beacon signal coming from the lost astronaut. You can see there's 4 sensors on the front of Saver. The 3 that are all the same are PIR sensors. Those can detect heat as well as motion. So if there's an object that has heat and motion, the sensor will pick it up. So that's going to be used to locate the astronaut who would be stranded in the water. The other sensor on the front is an ultrasonic sensor, and that detects distance. So once the Doppler antenna and then the PIR sensors find the astronaut, once you get into a closer range, the ultrasonic sensor will pick up on how far away it is from the astronaut so that it can stop at a safe distance before hitting them. The 2 motors on the back of Saver are used not only to propel it, but also to steer. So if Saver needs to turn right, the left motor will start going a little faster and the right one will slow down in order to make that right-hand turn. And lastly, you can see that there are foam bumpers around the outside of Saver. This is not only to protect the device during testing, but also to protect the astronaut in case it does get a little too close, and it kind of helps with the edges to not be as sharp.
By the end of the semester, our team expects to fulfill the objectives of this competition by fully constructing the waterproof hull out of 1/8-inch polycarbonate. The shell of the Saver will be held in place using epoxy and a notched interlocked polycarbonate to prevent fracturing or leaking due to impact. The electronics will be integrated to allow for accurate beacon locating and autonomous motion. All sensors will be implemented to the Arduino controller to locate, travel, and stop within 5 feet of the beacon signal. For the Saver to be considered a success, the machine will be sturdy enough to be dropped into a maritime environment, buoyant in water and waterproof, receive the astronaut signal, travel to that signal, and safely provide access to a radio, a life vest, a medical kit, and fresh bottled water to the astronaut in distress. Visit the project website linked in this page to see how the project turned out.
Hello, everyone. I'm Reese Van Dorn. I am head of the electrical development for this project. And I'm going to go over an initial issue we had with our radio direction finding system, as I'll play this video here. So you can see in the background there, I start off in the middle. The bearing is okay, but then it starts to wander it thinks I go behind it even though I'm off to the side. And it just goes crazy, and I come back to the middle. Same thing, just is not stable at all. Like that bearing should be pointing right directly towards me and not wandering. So obviously that is not suitable for a rescue situation. And the issue we ran into in the sticky detail that I'm going to go over is the receiver. So we initially wanted to use a software-defined radio, as pictured on the left there, and it was very inexpensive and interfaced nicely with the Raspberry Pi, just plugged in via USB. That was part of the issue, is that USB is not very robust. So you bump that thing or have any shock and it comes loose, you lose your signal. So obviously that wouldn't work for a 15-foot drop into water. And the other issue too is what you saw in the video there, where the Raspberry Pi does some background function and it completely screws up the RDF system and it just goes haywire on you. Now the solution was, and what we had to work out, was to go with just a off-the-shelf regular receiver, conventional receiver. The biggest issue there was it was a major risk to our budget, because we were already getting to the end of it, since we already purchased almost everything, and this receiver was very expensive. So our purchaser had to coordinate with the MSD office, make sure we still had room in our budget and we could return some things like that dongle and the Raspberry Pi to help fund getting this receiver now. The very nice thing and good attributes about it were that it's a standalone operation. So we don't have to configure Raspberry Pi and set up what bandwidth we want to pass. It just detects the signal on its own and passes it to our radio direction finder. And the connection is very robust because it uses BNC connectors. As you can see, there's that little silver connector where it screws and latches on nicely. There's no way it's coming loose in any situation. And it's a dedicated receiver. So it's dedicated to receiving signals and transmitting it out, out of either its speaker or its headphone jack, which is what we're using in our case. And it won't do a background function and wander to something else, and mess with our bearing. So we have a very stable bearing now. And so lessons learned here were your design is never really finalized until you've done extensive testing, and prototyping. So your design can continue to kind of morph itself until all the requirements are met.
We would like to thank NASA for creating this year's Micro-G Next Challenge, as well as RIT's MSD department for providing us the resources we needed to make this concept a reality. We would also like to thank Alan Dawson, Elizabeth DiBartolo, James Stefano, Kathleen Lampkin-Kennard, and Donna Rankin-Perobek for generously providing their time and knowledge to the team. Thank you.